Hi, this is Dr. James Wood, and welcome to Psych 1303 Statistical Methods. Today's lecture is going to be on surveys and polls. In particular, we're going to talk about populations, samples, and the sampling distribution. Now, let's begin by reviewing what we talked about last time, which was a lecture on probability theory. Remember, we began by talking about Blaise Pascal, the French mathematician who contributed the most to the early development of probability theory. I told you he was probably a saint. He was also a philosopher and scientist. He laid the basis for some of the things I'm going to be showing you here today. We said modern probability theory has many applications in the present day world. And to name just a few, these include gambling, public health, and research statistics. Now, during the last class, I explained that probability has been called the science of uncertainty. I told you about a famous example where a mathematician predicted the number of deaths from horse kicks in the Prussian army, even though there was complete uncertainty about which particular soldiers would be killed by a horse. There was almost perfect certainty that the overall pattern of deaths in the army would follow the Poisson distribution. During the last class, I introduced you to the frequentist definition of probability, which is the definition most commonly used by mathematicians. This definition begins with some procedure, event, or situation that's repeated many, many times. And each repetition is called a trial. The procedure or event results in, each trial, let's put it this way. Each trial results in one or more possible outcomes, and each outcome occurs in a certain percentage of the trials. The percentage of trials that an outcome occurs is the probability of the outcome. Now, in the last lecture, you also learned about some basic ideas about probability theory. We began with some mathematical notation. A capital P followed by something inside parentheses means the probability of this thing in the parentheses. For instance, capital P followed by an A inside parentheses means the probability of A, or the probability of outcome A. Then we focused on the probabilities of dichotomous variables, which we're going to be dealing with during the next 3 weeks. If a procedure has only two possible outcomes, we can use a dichotomous variable to represent each outcome. Each outcome has its own probability. For instance, we can have the probability of heads and the probability of tails. We often use the letters A and B to represent the two outcomes. So we have the probability of A and the probability of B. If we use A and B to represent the two outcomes, then the probability of A, P with A inside parentheses, is the probability of the first outcome, and the probability of B is the probability of the other outcome. We use the small letter P to represent the value of the probability of A. And we use the letter Q to represent the value of the probability of B. There are several important things to remember about P and Q. First, P is always between 0 and 1, and that's including 0 and 1. And the same is true for Q. If P equals 1, then outcome A is certain to happen. And if P equals 0, then outcome A never happens. Other values between 0 and 1 are also possible. The closer the probability of an outcome is to 1, like 0.95, the more likely that outcome is to happen. So 0.95 is very likely to happen, but not certain. The closer the probability is to 0, like 0.05, the less likely it is to happen. So if P equals 0.05, then A is very unlikely to happen. It's rare, though it might happen at some time. Another important fact about P and Q is that P plus Q always equals 1. And another related fact is that Q equals 1 minus P. Now, this second fact is particularly useful because if we know P, we can always find Q just by subtracting P from 1. For instance, if we know that P equals 0.75, then we automatically know that Q equals 1 minus 0.75, which is 0.25. We use P and Q when we're dealing with a Bernoulli variable. A Bernoulli variable is a dichotomous variable whose values are either 1 or 0. The mean and standard deviation of a Bernoulli variable are easy to find. The mean is equal to the proportion of observations that are ones, and it's also equal to P. There are two ways to calculate the standard deviation of a Bernoulli variable, the long way and the fast way. If we do it the long way, we calculate the deviations, the squared deviations, the mean square and root mean square, and we do this for all the values of the observations. In other words, we can calculate the standard deviation of a Bernoulli variable exactly like we do any other variable. But if we do it the fast way, the standard deviation of a Bernoulli variable is equal to the square root of P times Q. And this is a shortcut we can use with Bernoulli variables, but not other variables. In the last lecture, I recommended that you memorize these equations for the mean and standard deviation of a Bernoulli variable. They'll come in handy during the rest of the course. The mean of a Bernoulli variable equals P, and the standard deviation of a Bernoulli variable equals the square root of P times Q. Okay, so that's what we covered last time. Now we're ready for some new material. Today we're going to learn about the statistics of political polls and surveys. Political polls are usually conducted during election years to find out how many people favor one candidate, like Bernie Sanders, over another, like Joe Biden, when they're running for president, senator, or some other office. Surveys are a lot like political polls, but their purpose is usually different. Surveys don't typically ask about how people are going to vote. Instead, surveys ask about other topics. For instance, a health survey might try to find out how many people get physical exercise each week, or how many are using their seatbelts. A sales survey might try to find out how satisfied people are with their current wireless phone service. To understand the logic of political polls and surveys, we need to understand populations, samples, and sampling distributions, which are the main topics today. So what do we mean here by a population? A population is defined as all the members of a designated group. For instance, the population of U.S. residents consists of all people who live in this country and make it their primary residence. The population of El Paso eligible voters consists of all people living in El Paso who are eligible to vote. A population doesn't have to consist of human beings. For instance, biologists study populations of animals all the time. The population of coyotes in El Paso County consists of all coyotes who live within the county boundaries. Next, let's talk about a sample. A sample is defined as a subgroup of a population that is selected for purposes of gaining information about the population. For example, let's say I'm interested in the population of all El Paso voters and how they're going to vote in the next election. To gain this information, I might interview the first 100 voters I meet in the El Paso Plaza. These 100 voters are my sample. Or I might call up 1,000 voters on the phone. In this case, the 1,000 voters I call are my sample. As another example, let's consider the population of all UTEP students. That is, all students at the University of Texas at El Paso. This population includes all the 23,000 or so students enrolled at UTEP. I can decide to find out about these students by selecting a sample. For example, I might give a questionnaire to the students in my statistics class. Unfortunately, this sample would not resemble the whole student body very well because most students in my statistics class are psychology students or kinesiology students. On the other hand, most UTEP students are not majors in psychology or in kinesiology. So when a sample resembles the population it comes from, we say it is a representative sample. When it does not exactly resemble or is special in certain ways that set it apart from the population, we say the sample is a non-representative sample or unrepresentative sample. My statistics class is not a representative sample of UTEP students. Now, as I said, a population doesn't have to consist of human beings. For instance, the population of health supplements consists of all the health supplements that are sold in drugstores, convenience stores, or any place else. If I want to study these health supplements, I could go out and randomly buy 100 bottles of different health supplements at different stores. These 100 bottles would be my sample of healthcare supplements, and I can study my sample to gain information about health supplements in general. In fact, a well-known study of health supplements was conducted a few years ago by collecting a sample of bottles from various stores around the country and studying them. And it was found that many so-called health supplements are bogus. They don't contain the substance they claim to contain, or they hold it only in a very small amount with a lot of filler. The way that surveys and political polls work is that they gather information about a sample to learn about a population. For instance, a political poll might interview a sample of 500 Texas voters to learn which candidate for Senate is favored by the entire population of Texas voters. The Nielsen Company studies the television viewing behavior of a relatively small percentage of Americans. And from that small sample, the company estimates which television shows are most popular among the entire population of American television viewers. And as I said, not all surveys are about people. For instance, the Department of Fish and Wildlife may gather a sample of fish from a lake. Based on that sample, the department can learn about the entire population of fish in a lake, how big they are, and how healthy. This week, we'll be focusing on the statistics of political polls. And this is a good way to learn about the ideas that underlie all surveys and polls. The example we'll be using involves the political polls about Christina Green, who is running for governor of East Virginia. Now, this example is totally made up. There is no state called East Virginia. There really is a state called West Virginia, but there's not any East Virginia. However, this fictional example will help us to understand how political polls and surveys work. There are 800 million non-existent voters, let's just say 8 million fictional voters in the fictional state of East Virginia. And the question that any political poll wants to answer is this: how many of these voters plan to vote for Christina Green? The 8 million voters of East Virginia are called the population of interest because this is the population that all these political polls want to know about. To find out about this population, a pollster, that's a person who conducts polls, a pollster interviews 1,000 randomly selected voters and learns how many plan to vote for Green. These 1,000 voters are the pollster's sample. By the way, it's a good thing that the pollster's sample is randomly selected. The pollster selects voters at random, maybe from the state's list of registered voters, to ensure that the sample is representative of voters in the entire state. Remember, we said before, you really want a representative sample. Random selection is an effective way to make sure that the sample is representative of the population as a whole. So if you want a representative sample, random selection is probably your best way to go about it. The pollster finds that 54% of the voters in the sample plan to vote for Green. We will say that P equals 54%. Now, you might recognize this symbol P. We've run into it before, haven't we? Here, P is the symbol that stands for the proportion of voters in the sample who plan to vote for Green. Now, if we use P to represent the proportion of voters who plan to vote for Green, what symbol do you think we'll use for the proportion of voters who do not plan to vote for Green? Give you a second to think about that. You got it? P are those who vote for Green. What symbol do we use for the voters who don't vote for Green? Aha, you got it? It's Q. Q is the proportion of individuals in the sample who do not plan to vote for Green. Now, of course, we ran into these symbols P and Q before when we discussed Bernoulli variables, and we can use a Bernoulli variable to indicate whether voters plan to vote for Green. A 1 indicates a voter who plans to vote for Green. A 0 indicates a voter who does not plan to vote for Green. Now, I don't want you, no, excuse me. So I'm going to give everybody a chance to think a minute. If 54% of the voters in the sample plan to vote for Green, what is Q equal to? Got it? Okay. If 54% plan to vote for Green, then the other 46% must not plan to vote for her. That's Q. Q is 46%. With Bernoulli variables, Q is always equal to 1 minus P. Now, in this case, we're using percentages instead of proportions, so Q is equal to 100% minus P. Here's a new symbol. It's the Greek letter pi. Pi is the Greek p. Now, in geometry, this symbol means the ratio of a circle's circumference to its diameter. But when we're talking about populations and samples, pi stands for something different. Pi represents the proportion of voters in the population of interest who intend to vote for green. So what's the population of interest here? Yes. Okay, you've got it. The population of interest is all 8 million East Virginia voters. So pi is this number, 55%. Oh yeah, I haven't told you that. 55% of East Virginia voters plan to vote for green, so pi equals 55%. Sorry, I'm getting a little mixed up with these slides, but you can see. So pi is the proportion. You might say it's, yeah, okay. So 55% is the proportion of voters in the population who plan to vote for green. That is, pi equals 55%. Now, you remember that P equals 54%. P is the proportion of voters in the sample of 1,000 voters who intend, in the sample of 1,000 voters who intend to vote for green. So 54% is the proportion in the sample, 55% is the proportion in the 55 is the proportion in the population. And you can see these two numbers are close, but they are not identical. The proportion in the sample is only an estimate of the true proportion in the population. It should be close, but it probably won't be a perfectly accurate. Estimates generally are not perfectly accurate, but they're supposed to be close. Now, in this case, the estimate is off by negative 1%. It's 1% too low. This negative 1% is called the sampling error. It's the amount that it's off. Sampling error is the amount that the estimate from the sample, that is P, is off from the true value in the population, which is pi. Just a second, I have a phone ringing. Just turned it off. Sorry. I should turn off my sound, but then that would interrupt this lecture. So we'll see if it rings again. Okay, so we just defined the sampling error. We put it mathematically. Sampling error is defined as P minus pi. Now, okay. Now, in sampling error, the word error does not indicate that something is wrong with the poll. If the very best pollster in the world conducts an extremely careful political poll, the results of the poll will still be off a little. Sampling error is inevitable in polls and surveys. It means you just can't avoid it, no matter how good your survey or your poll is. Sometimes sampling error is called the luck of the draw. Now, to see why it's inevitable, think of what happens, or think of what would happen if you draw 10 cards from a deck of cards. In this case, the population is the deck of cards. There are 52 cards in the population. And we know that half the cards in the deck are red. That is, they're either hearts or diamonds. The 10 cards that you draw are your sample. However, even though half the cards in the deck are red, we don't expect that is, half the cards in the population are red. We don't expect that 5 of the 10 cards we draw will necessarily be red. That is, we don't expect that we'll get half in, even though we have half red in the deck, we don't necessarily expect expect half red in our sample. Sometimes 5 of the cards we draw, of the 10 cards we draw, will be red, but there are going to be times when 6 of the cards we draw are red, and sometimes there are only 4 of the cards are red. And this is what we mean by luck of the draw. Even though pi in the deck of cards is 50%, that is, we have 50% red cards in the deck, we don't expect that p, the proportion of red cards in the sample of 10 cards, will always be exactly 50%. We don't say, I drew 6 red cards out of 10, the deck must be rigged. So p gives us an idea, an estimate of pi, but it's not perfect. Sampling error is bound to happen. So let's practice how to calculate sampling error for several samples using this formula. This table shows the results of 10 political polls that have recently been taken in the state of East Virginia. In each poll, a pollster interviewed 1,000 voters. Now, we're assuming we already know the true proportion of voters in the state is 0.55. In other words, pi equals 0.55 or 55%. Here are the results for the first 3 polls. Now, in the first poll, what proportion of voters in the sample said they planned to vote for green? Okay, here it is. There's sample 1, 1,000 people in the sample, and P equals 0.543. That means of those 1,000 people, 0.543 said they were going to vote for green. Of course, 0.543 of 1,000 is 543, but we're not looking for the number, we're looking for the proportion. How about in the second poll? What proportion of the people, of the voters, said they were going to vote for green? Take a second, look at it. Okay, it's 0.567. And finally, what proportion said they were going to vote, in the third sample said they were going to vote for green? That's right, it's 0.557. Now, for the first sample, the table shows that the sampling error was negative 0.007. How did we get that number? Well, remember, here's the formula up here. We subtracted pi from p. So we subtracted 0.55 from 0.543, and we got negative 0.007. For the second sample, we see that p is 0.567, and go ahead and calculate this out. You notice the table says that the error was 0.017. So let's see. No, just a sec. It's 0.017. So let's go ahead and check. Get a calculator and check out. Subtract pi from p, and I'll give you about 15-20 seconds to do that. Okay, checked it out. Okay, now we have another one here. For sample 3, P is 0.557. Make the calculation yourself for sampling error and see what you get. Okay, we can do the same thing with all of them here. So I already did that. I'm not going to have you check my work on this, but I did want you to have a little practice calculating sampling error, subtracting pi from p. So you can see for every sample, we can calculate sampling error. Each sample has its own sampling error. So each sample has its own value of p. Each sample has its own sampling error. Now we're ready to talk about the sampling distribution. And this is probably the most important concept of the next 3 weeks. In fact, I'd say it's the central idea for the next, say 3 classes, in classes we're going to have. Today and during the next 3 weeks, you're going to learn a lot of new concepts and terms that help you to understand about sampling and political polls, and they're all related to a sampling distribution. So here's a list of some of the things that are all related to the sampling distribution. You've already learned the first three today. You learned what a sample is, what a population is, and what sampling error is. So we're already learning concepts that are related to the sampling distribution. Also, during the next 3 weeks, you're going to learn ideas that help you make use of the sampling distribution, because sampling distributions are so useful. Now, in class today, I'm going to explain, I won't go through the whole list of all these things that are coming up. You'll see them when they come. But, and today I'm going to explain the sampling distribution, but I have a suggestion for you. Don't just rely on this lecture. This is such an important concept that after you hear the lecture, I recommend you go read about sampling distribution in your assigned readings, and then do the homework problems and do them now. Don't wait on this, because if you learn now what the sampling distribution is, you're going to find the next lecture and the next 3 weeks of lecture very understandable and interesting. If you don't learn about the sampling distribution now, if you leave it for a week or two, then the next few lectures are going to be quite confusing. So the easiest way to explain what the sampling distribution is to explain how it's made. This will be helpful. So for sampling distribution, we're going to imagine we are drawing a very large number of different samples from a population. The number of samples we're going to draw is called K. K is the number of samples. Now, in the example we'll be using, K is 700. That means we are going to draw 700 different samples. Each of these samples includes the same number of individual people. N is the number of individuals in each sample, and N is always the same for each sample. Now, in the example we'll be using, N is 1,000. This means that the number of individuals in each sample is 1,000. So we have 700 samples, and each one includes 1,000 different individuals. Okay, now let's talk about how to make a sampling distribution. There are 5 steps to make a sampling distribution. First, we begin with a large population. Let's say it should have 1 million or several million individuals in it. So when we talk about the state of East Virginia with 8 million voters, that's large enough, and that'll be our sample. Second, we collect a large number of samples from this population. The number of samples is called K. Now, when we say K is a large number of samples, what's a large number? Well, we'll talk more about that later in later lectures, but I would say for now, K should be at least 700 samples and more if possible. So in the example we're using, we'll imagine that K equals 700. So pollsters, let's say what we're saying is pollsters conduct 700 different polls in East Virginia, and each poll has its own separate sample. Now, of course, this is not realistic. No election in a single state has 700 different polls, but you can at least imagine it happening, and that's what we need because we're using an imaginary example. Now for the third step. Each sample must include exactly the same number of individuals. We call this sample size n. Now, n can be any number. So it may be that each sample has exactly 10 individuals, or it may be that each sample has 100 individuals. As we'll see, there are good reasons to have at least 30 individuals in each sample. But technically, the only requirement for a sampling distribution is that each sample has to have exactly the same number of individuals as the other samples do. You cannot have some samples 10 individuals and some samples with 100 individuals. The sample size must be the same for each and every sample. Now, in the example we're using, we're assuming that n equals 1,000. So each sample includes exactly 1,000 individuals. Next, we have to calculate p separately for each of the 700 samples. So this will take 500 years or so because there's 700 samples and we've got to go and calculate p for each. Let's get started. Here are the first 17 samples entered in an Excel sheet. For each sample, the proportion of voters who plan to vote for Christina Green has been entered. So the first column is sample numbers. We have sample 1, sample 2, sample 3, sample 4. The second column has the p for that sample. So for the first sample, p is 0.543. For the second sample, it's 0.0567. For the third sample, it's 0.557, and so on. Now, we'll just keep doing this for every sample here. For you see, sample 18 was the p was 0.550, which meant since they have samples of 1,000, it meant there were 550 voters who said they were voting for Green out of those 1,000. For sample 19, p was 0.529. We just keep doing it. Here we go, sample 36, p was 0.539. For sample 37, it was 0.556. Boy, it just keeps going, but let's skip down to the bottom. Okay, here we are, the last. We're exhausted. We've been calculating p for all these samples. Now we get to the bottom. We can see that for sample 699, the p was 0.552. For sample 700, the p was 0.530. Well, thank goodness we're done with that. So what we end up with is a really long column of numbers. Each number represents p in a different sample. Now, obviously, I can't show all the numbers here on one slide. It would take forever. But how many different numbers are there in this column? Okay, that's right. There are 700 numbers in this column, and each represents the value of p in a different sample. In this column of numbers, these 700 numbers are what we're going to use to construct the sampling distribution for p. And we're going to do that in step 5. In step 5, we take all those values of p from the 700 samples and we plot them as a histogram. This histogram shows the sampling distribution. And here it is. Ta-ta! The x-axis represents p, the proportion who intend to vote for Green. Let's see if I can. Well, no, it's not working. I'm trying to get a pointer in here, but it's not working. So along the bottom, right, the x-axis, that represents the proportion who intend to vote for Green. The y-axis on the side represents the percent of samples that had a particular value of p. In a way, it looks like lots of histograms you've seen before in this class. What makes this histogram different is that it doesn't represent individuals. It represents samples. That's why it's called a sampling distribution. It shows the distribution of p in 70 different samples. Now, eventually you're going to be very comfortable with sampling distributions, but right now, seeing the first time, it can be a little puzzling. So I'm going to ask you some questions that will help you to understand the sampling distribution. And for these questions, uh, uh, I do want you to stop and think about each one. So here's the first question. In the 700 samples, what was the highest value of P? Here's the sampling distribution so you can look at it as you think. And I'll repeat the question. In the 700 samples, what was the highest value of P? And remember, P is the proportion of voters in a sample who plan to vote for green. So I'll give you a second. What was the highest value of P? Okay, here it is. I marked it on the right side in pink. This sample over here is one with the highest P because P is close to 0.61. We can see that on the x-axis. So in other words, in this sample, nearly 61% of the individuals plan to vote for Christina Green. So that means this particular sample, 610 voters said they'd vote for her. And what does that leave us with? That's 390 who said they would not. I'm sure Christina Green is happy about this. Okay, now, here's the next question. In that sample, with the highest value of P, what was the sampling error? So here's the sampling distribution again, and I'll repeat the question. In that sample on the right-hand side with the highest value of P, what was the sampling error? You might need a calculator or you might be able to get it. If you remember, pi is 0.55. Okay, here's the answer. Sampling error equals P minus pi. P is 61. Pi, that's the proportion in the whole state who intend to vote. Remember, that's in the population, that's 0.55. And so the sampling error is 0.06. So this sample with 0.61 overestimates what's happening in the state by 0.06 or 6 percentage points. So here's another question for you. In the 700 samples, what was the lowest value of P? Here's the sample again, and here's the histogram again, and I'll repeat the question. What was the in these samples? What was the lowest value of P? Okay, there it is. I just highlighted it on the left-hand side in pink. There was this one sample way on the left that had a P of, it looks slightly less than 0.50, but we'll call it 0.50, just to simplify things. Now, in this sample, about 50% of voters said they, less than 50% of voters, well, let's say about 50% of voters said they planned to vote for Christina Green. And go ahead, what was the sampling error for this sample? Remember, pi is 0.55. Okay, so for this sample, P minus pi is 0.55 minus 0.50. No. Got that wrong. It's 0.50 minus 0.55, which is negative 0.05. It's negative because the sampling error is let's put it this way, 0.50 is less than 0.55. But of course, we ran into this before with deviations, right? And z-scores. When you go to the left side, they turn negative. And it's the same with sampling error. So here's another question. What value of P was most common in the samples? So here it is. Which value of P was most common in the samples? In other words, where are the most samples that have a single value of P? What value of P is it where there's lots of samples? Well, it's this bar here. See, it looks like it's around 0.54. I marked it with the red arrow or 0.55. That bar, let's see, about 14%. If we look over at the y-axis, we can see that that's about 14% of the samples had a p around 0.54 or 0.545. So this was the value of p that was most common. Now here's a true-false question. True or false? There were more samples with p close to pi than there were samples with p far from pi. So here's our distribution. The question is true or false? There are more samples with values of p are close to pi than there are samples whose values of p are away from or distant from pi. Far from, yeah, pi. Is that true or false? Okay. The answer is there are definitely a lot more samples. Let's go back. See, true or false? Yes, it's true. There were more samples with values close to whose value of p was close to pi than there were samples whose values of p were far from pi. And we can see in the middle, there are where all the tall bars are, those are samples whose value of p was 0.54, 0.55, and those are really tall bars. So there are lots of samples whose value of p is close to pi. But if we look on the left side or the right side of the graph, we get far, there's pi, yeah, sorry. If we look to the right side or to the left side, we see that there are very few samples whose value of p is far away from pi. And this will turn out to be something important to us later on. In most samples, p is going to be close to pi. We don't get nearly as many samples where p is far away from pi. Now, here's another question. The average value of p in the samples was about equal to pi. Is that true or false? Let's see. I don't have a separate question for this, but let's ask you again. The average value of p in the samples was about equal to pi. Is that true or false? Okay, it's true. As you can see, the values of p are distributed normally or approximately normally. And in a normal distribution, the mean is at the center, which is somewhere around 0.55. So the average value of the p's is approximately equal to pi. In fact, in a later lecture, we'll learn that the average value of the p's is going to be exactly equal to pi, always. But we'll come back to that later. Okay, now for a toughie. What is the standard deviation of p in the samples? Let's just take a look at it again. What's the standard deviation of p? Okay, the correct answer is that the standard deviation of the values of p is 0.015 or about that. Now, that was kind of unfair of me because I haven't really taught you how to do this before yet, but you're going to learn now. I'm going to show you how to estimate the standard deviation from a histogram when that histogram is kind of sort of normally shaped. And we'll be using this distribution. So if we're looking at that distribution, how do we come up with a number that at least estimates the standard deviation of the variable? The variable in this case is p. Well, first, we need to estimate the mean. Actually, in this case, we don't have to estimate it. I've told you several times, the mean is 0.55. Okay, so we got the mean, but normally, if you don't know it beforehand, you just look at the graph and choose the value that looks like the mean to you in the middle. And you don't fret too much about being exact because you're just estimating. So you do make your guess. So we say the mean is probably 0.55. So next, we need to estimate the score at the 97.5th percentile. This is actually fairly easy. We look at the right side of the graph. We know the 97 score at the 97.5th percentile is the score that is greater than 97.5% of other scores. And if we look down that, we can see it's got to be at the right. It's probably about 0.58, maybe 57.5, maybe 0.58, 0.5, but we're going to say that it's 0.58. And that little squiggly equal sign means is approximately equal to. And remember, since it's estimation, we don't fret about it too much. We just do our best. So we've now identified the score at the mean, 0.55, and the score at the 97.5th percentile. Now, why did I ever choose that percentile? Well, we'll see in a second, because I want you to ask yourself, what are the z-scores for 0.55 and 0.58? So let's start with 0.55. What is the z-score for if the raw score, if p is 0.55? Well, here's the answer. Z equals 0, because 0.55 is at the mean, or at least we estimated it is. And of course, the mean is always equivalent to a z-score of 0. So now, what about the other score, 0.58? What is the z-score for that? Well, if you remember the earlier parts of the class, the z-score is 2. Way back the early part of the course, I said to memorize certain percentiles, including the 97.5th percentile. And as you remember, I asked you to memorize 97.5th percentile because it's equivalent to a z-score of 2. So when we selected 0.55 and 0.58 using the mean and the 97.5th percentile, what we were really doing was choosing the scores with a z-score of 0 and a z-score of 2. So now let's see where we're at. We just figured out when p equals 0.55, z is equal to 0. When p equals 0.58, z equals 2. So now we're ready for another question. How many standard deviations apart are 0.55 and 0.58? So look at this for a second and figure it out. Okay, here's how we do it. The answer is they are 2 standard deviations apart. Here's how we figured it out. A z-score of 0 and a z-score of 2 are 2 standard deviations apart. We've been studying that since the beginning of the semester. They're 0.55 and 0.58 are equivalent to z-scores of 0 and 2, so 0.55 and 0.58 must be 2 standard deviations apart. So now we're ready for my final question. We figured that these 2 scores, 0.55 and 0.58, are 2 standard deviations apart. So now the question is, what is 1 standard deviation equal to? I'll give you a second to think about it. Okay, let's work it out. 0.58 and 0.55 are two standard deviations apart. So if we subtract 0.55 from 0.58, that equals 2 standard deviations. We could say the distance between 0.58 and 0.55 is 2 standard deviations. 0.58 minus 0.55 is 0.03. So 0.03 is equal to 2 standard deviations. 2 standard deviations are equal to 0.03, so 1 standard deviation is equal to half that, 0.015, which, I kind of tipped you off to at the beginning. But now you know how I arrived at that number. So now we know the standard deviation is 0.015. Let's go back to the histogram for a second, just so I can show you. There's the mean, 0.55. We add a bar, 0.015 to the right of the mean. We have 0.565. That's 1 standard deviation away from the mean. We can add a bar to the right of 0.565, which is 0.015 to the right, and we have 0.580. That's 2 standard deviations away from the mean. And we can add some bars to the left of the mean if we want to. And all these bars are 1 standard deviation apart from each other. Now, when I estimate the standard deviation from a histogram, when I'm just trying to figure out what the standard deviation is by looking at a histogram, I don't go back and draw in these bars. I'm drawing these bars because I want to show you so you'll have a clear picture of how a normal distribution looks when we draw in the mean and the standard deviations. Okay, now we're just about at the end. But before that, let's summarize what we did to estimate the standard deviation from a histogram. First, we estimated the mean and the score, the mean, which was 0.55, and the score at the 97.5th percentile, which is 58. And we did this because these two scores are equivalent to z-scores of 0 and 2. Second, we found the distance between these two scores. 0.58 minus 0.55 is 0.03, and this distance is equal to 2 standard deviations. And third, we divided the distance between the two scores by 2, and that gave us an estimate of the standard deviation. It's just an estimate. It's not exactly right, but all we want right now is an estimate. Okay, now, I am now going to sum up. We're just about at the very end. I want to sum up what we covered today to refresh your mind. Today we learned that a population consists of all members of a designated group. A sample is a subset of the population that we study to gain information about the population. We used political polls as an example. In polls, we use P, the proportion of voters in a sample who favor a candidate, to estimate pi, which is the proportion of voters in the entire population who favor the candidate. P, which is the value in a sample, is hardly ever exactly correct as an estimate of pi. P and pi are usually going to have a little distance between them. They're going to be a little different. And the difference between the value of P and the value of pi is called the sampling error. Now, today we also learned about one of the most important concepts in statistics, and it's going to be dominating this class for the next 3 weeks. It's the sampling distribution. And I explained how a sampling distribution can be formed. First, you start with a large population. Second, you draw k different samples from the population, and k is always very large. 3, each sample has n individuals in it. 4, you calculate p in each of the k samples. And 5, after you have a large value of p, you graph these values. There's a lot of values of p that you have. You graph them as a histogram, and that's the sampling distribution. Now, finally, what we did was we learned how to estimate the standard deviation of a sampling distribution or any normal distribution by looking at a histogram and making an estimate. Okay, so it's been a challenging day today, but you've made a start on something of real value. Next time, we'll learn more about political polls and surveys. See you then.